Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
For the better part of a century, really. When astronomers look out at the universe, they've been working with a kind of standard cosmic blueprint.
The lambda CDM model, yeah.
Exactly. And if you followed cosmology at all, you know this blueprint is, well, it's deeply unsettling.
It is a bit strange, yeah.
Because it says that everything we see, the stars, planets, gas, the stuff we interact with.
Normal matter.
Right, normal matter. Makes up less than 5% of everything that's out there.
That's the picture, yes. The huge majority, like 95% of the universe, is completely theoretical. It's unseen, undetectable directly anyway.
And then 95% is split, right?
Correct. Between cold dark matter or CDM, which acts like extra gravitational scaffolding.
Holding galaxies together, essentially.
Holding structures together, yes. Yeah. And then there's lambda, the Greek letter lambda. That represents dark energy.
The mysterious push making the universe expand faster and faster.
That's the one. It's this repulsive force driving acceleration. The model, mathematically, it actually works incredibly well for describing observations. But, the big but is that it requires us to accept that reality is fundamentally dominated by these two components that we just cannot find. We haven't detected them directly.
And that huge puzzle is what we're diving into today. We're exploring a really radical new hypothesis.
Truly radical, yes.
It suggests this entire dark sector, this, 95% needed to make the standard model work. Maybe it doesn't actually exist.
Not as substances, anyway.
Right. Maybe it's just a cosmic illusion. We're looking at the work of Professor Rajendra Gupta from the University of Ottawa.
And he's really challenging the foundations here.
Totally. He's questioning the whole structure of modern cosmology.
His core idea, and it's a big one, is that what we interpret as dark matter and dark energy, they aren't mysterious particles or fields. Instead, they're just the effects we observe. Because the basic strengths of nature's forces, think gravity, electromagnetism, are actually slowly weakening over cosmic time.
Weakening.
And varying. And varying subtly as the universe expands and ages. This is huge because physics has always assumed these fundamental constants are just that constant, immutable.
Wow. So, okay, this isn't just tweaking an equation or looking for a new particle.
Well, no. Far beyond that.
This is proposing that the actual rules of the physical universe might be evolving, changing over billions of years.
That's the proposition.
Before we get deeper into how this works, let's just clarify the names. You mentioned lambda CDM as the standard. What's the alternative framework Gupta is putting forward called?
Right. The new model is called CCC plus TL Cosmology. It's quite a mouthful, I know.
CCC plus TL. Okay. Let's break that down. What do those letters stand for?
Absolutely. It's technical but crucial. CCC stands for covariant coupling constants.
Covariant coupling constant.
That's the key mechanism. It means the fundamental constants like G, the gravitational constant, or C, the speed of light, aren't fixed numbers. They change slowly, they covary as the universe gets older.
So if gravity was, say, slightly stronger billions of years ago than it is now?
Exactly. That changes everything. Yeah. How we interpret distances, how we measure cosmic time, all of it gets recalibrated.
Okay, that's the CCC part. What about the TL?
The TL stands for tired light.
Tired light. That sounds familiar. Isn't that an older idea that was mostly discarded?
It is, but this is a modified version, integrated with the CCC part. The basic tired light idea was that light loses energy just by traveling vast cosmic distances.
Making it look redder, redshifted.
Precisely. In this CCC plus TL model, the redshift we see from distant galaxies isn't only because space itself is stretching, which is the standard view.
Right, the expansion of space.
Instead, it's partly due to this intrinsic energy loss, plus the effects of the covariant constants. It's a combined effect. Gupta uses this combination to fundamentally reset our cosmic measuring tape.
Okay, I see. So if the constants aren't constant and redshift isn't purely expansion, then our whole map of the universe, its size, its history, it all has to be reevaluated.
Completely reevaluated.
So let's get into the core claim then. If these forces are changing, how on earth does that explain both the accelerating expansion of the universe and the weird way galaxies rotate? These seem like totally different problems on vastly different scales.
And that is the central issue with lambda CDM, isn't it? And it's precisely the main attraction of the CCC plus TL idea. Standard cosmology needs those dark components because we have these two distinct sets of observations.
One huge, one relatively small.
Exactly. Observations on completely different scales that just don't fit if you only use the visible matter we see. And crucially, lambda CDM needs two totally different fixes conceptually and mathematically for these two problems.
All right, let's tackle the big one first. Dark energy. This operates on the cosmological scale, right? Looking at the universe as a whole, where things are assumed to be sort of uniform.
Precisely. We're talking scales larger than, say, 600 million light years across. On that scale, the universe looks statistically homogeneous. Basically the same everywhere, smooth, uniform.
And the standard model observation there is
that the expansion of the universe isn't just happening, it's speeding up. It's accelerating.
Which is weird, like throwing a ball up and having it go faster and faster instead of slowing down.
That's the analogy, yes. It defies gravitational intuition.
Yeah.
So, to explain this, standard cosmology introduces dark energy, lambda. It's effectively an unknown repulsive force, maybe an energy inherent to empty space itself, pushing everything apart.
It's basically a fudge factor then, something added to the equations to make them match the observation of acceleration.
Well, it's a parameter added to Einstein's equations that acts like a repulsive force. Whether it's a fudge factor or a real physical entity is the big debate. But yes, it's put there specifically to explain the acceleration.
Okay, so that's the standard view. A mysterious push across the vast uniform cosmos. How does Gupta's model, with just weakening forces, achieve the same effect? No push needed.
It's a very neat substitution, actually. If the universe's fundamental forces, like gravity, are weakening on average uniformly across these vast scales as the universe expands, think about it. The overall gravitational pull that's trying to hold the universe together is getting weaker over time.
Like a stretched rubber band that's slowly dissolving.
Good analogy. The effect of this diminishing pull looks exactly like the effect of some external repulsive push. The universe appears to accelerate outwards, not because there's a stronger engine pushing it, dark energy, but because the brakes holding it back, gravity, are getting weaker.
That's clever, if flips a cause and effect. So the big-scale expansion problem is potentially solved by this global weakening of forces over time.
That's the proposal for the cosmological scale, yes.
So now we have to zoom way, way in, down to the scale of individual galaxies and clusters, the astrophysical scale. This is where dark matter is supposed to live.
We shift scales completely. Now we're talking about gravitationally bound systems, galaxies, galaxy groups. The universe here is not uniform at all. It's incredibly lumpy. Matter distribution is everything.
And the classic dark matter problem arises from how galaxies rotate, right? Stars on the outskirts are moving way too fast.
Way too fast. If you just count up the mass of the stars, gas, and dust, you can see there isn't nearly enough gravity to hold on to those outer stars. They should just fly off into intergalactic space based on Newtonian physics or general relativity alone.
So the standard fix.
The standard fix is to embed the visible galaxy within a huge invisible sphere, a halo, made of cold dark matter CDM. This invisible mass provides the extra gravitational pull needed to keep the outer stars orbiting quickly, matching observations.
Creating those flat rotation curves we observe.
Exactly. But it requires inventing a new type of matter, maybe a WIMP, a weakly interacting massive particle, something that has mass and gravity but doesn't interact with light, hence dark.
Okay, now the big question. How does the CCC plus TL model, with just its varying constants, generate that same effect? That extra gravity at the local galactic scale without needing any invisible matter halo?
Right. Here, the mechanism changes focus. It's not about the average weakening of forces over cosmic time anymore, which explained the dark energy effect.
Okay.
Now it's about the spatial variation of the forces within and around these lumpy structures like galaxies.
Spatial variation, so the strength of gravity changes from place to place within a galaxy.
In effect, yes. At the smaller, lumpy scale, the very presence and distribution of normal matter, the stars, the gas, the central black hole, causes the fundamental coupling constants themselves to vary locally, spatially.
So the constants aren't just changing smoothly over billions of years, they're also fluctuating depending on what matter is nearby.
That's the idea. And this localized spatial variation in the constants generates an effect that modifies gravity, providing the extra pull that we currently attribute to dark matter.
Hold on, I need to make sure I've got this straight. And for everyone listening, on the huge cosmic scale, the forces weaken uniformly over time. mimicking dark energy.
Correct, like a global average trend.
But zoom into a lumpy galaxy, and the forces vary in space, reacting to the clumps of normal matter, mimicking dark matter.
That's the crucial distinction. The effect arises from let's call them gravitational field modifications, generated by these spatial fluctuations of the constants around dense objects.
This is where it gets really interesting and potentially very powerful, because in the standard lambda CDM model, you need two completely different mathematical tools, right?
Absolutely different. You use cosmological fluid equations and the Friedmann equations to handle lambda dark energy on large scales.
And for dark matter.
For dark matter halos and structure formation, you need complex n-body simulations, tracking millions of hypothetical dark matter particles interacting gravitationally. Totally separate physics, separate simulations.
But Gupta's CCC plus TL approach
claims to explain both the cosmic acceleration and the galactic rotation curves using the same underlying physical principle and the same core equation.
Wow.
The unity comes from this single idea. The effects we observe are just emergent properties of fundamental constants, varying with cosmic age and local density. You don't need to add two separate, mysterious ingredients to the cosmic soup.
So instead of inventing a particle, CDM, and a field, lambda, Gupta says it's all down to one principle. The rules of physics aren't fixed.
They're dynamic.
That has a certain elegance to it, doesn't it? It simplifies things massively, conceptually at least. It changes the question from what new stuff is out there to how constant are the rules we thought we knew.
Precisely. And that kind of theoretical economy is very appealing in physics. If a theory can unify disparate phenomena with a single underlying mechanism, it gains a lot of attention. It suggests maybe 95% of the universe's observed behavior isn't due to unknown components, but arises from the dynamics of the 5% we can see and its interaction with evolving laws.
Okay, let's dig into that mechanism a bit more, especially for the galaxies. Because explaining those rotation curves without dark matter is notoriously difficult for modified gravity theories. How does this variation of constants actually create this gravitational imposter?
This involves a key mathematical parameter that emerges from the theory, usually denoted by the Greek letter alpha. Alpha.
Okay, is alpha a particle, a field?
Neither. Think of Belby as a mathematical term, a parameter that represents the effect of the evolving constants within the gravitational field equations. When you allow the coupling constants to change over time and vary in space according to the CCC plus TL framework, this alpha term naturally appears in the math.
So alpha quantifies the gravitational effect of the changing forces.
You could put it that way, yes.
Yeah.
It quantifies the modification to standard gravity caused by the varying constants.
And how does this mathematical term manage to do the job of a massive halo of invisible matter? How does it provide that extra pull?
Effectively, alpha inserts itself into the gravitational equations. It acts like an extra term that modifies the strength of gravity, but crucially, its strength depends on the local conditions.
Okay, so it's not a uniform effect.
Not at all on the local scale. This alpha term provides the needed extra gravitational influence to explain both the flat rotation curves in galaxies and, when treated differently on large scales, the cosmic acceleration.
The key must be how alpha behaves differently depending on the scale, right? A standard dark matter halo is usually pictured as this big, smooth, relatively static blob of stuff.
Right. CDM halos are generally modeled as smooth distributions, largely independent of the visible matter within them.
But if alpha comes from evolving constants interacting with normal matter, its effect must be tied directly to where the normal matter is.
Exactly. That's the critical difference. Alpha is dynamic and highly scale-dependent. On the huge cosmological scales where we dealt with the dark energy problem, we can approximate the universe as uniform. So alpha is treated essentially as a simple constant value there.
Determined by fitting data, like from supernovae.
Correct. Assuming homogeneity lets us treat it as a single number for the whole universe at a given cosmic time.
But then you zoom into one specific galaxy, you've got stars, gas, a black hole maybe? The matter distribution is incredibly clumpy, not uniform at all.
Extremely non-uniform, and that's where alpha gets interesting locally. At this astrophysical scale, alpha itself varies significantly in space.
Why?
Because its value, its strength, arises from the interplay between the evolving constants and the local concentration of standard matter. So the gravitational modification generated by alpha depends heavily on how much normal stuff is nearby and how it's arranged.
So alpha isn't some independent halo. Its effect is directly coupled to the visible matter.
Precisely. It's not an added substance. It's a modification of gravity induced by the normal matter within the context of evolving constants.
Okay, and this leads to what sounds like a really counterintuitive prediction, something about an inverse relationship with density. Can you explain that again? Because normally more mass means more gravity, simple as that.
Right. This requires a bit of a mental shift. We're not adding extra mass here. We're modifying the gravitational field itself. The theory predicts this inverse relationship. In regions where you have a very high density of normal, visible matter, like the dense inner core of a galaxy.
Where gravity from stars and gas is already really strong.
Exactly. In those regions, the additional gravitational effect caused by this alpha mechanism is actually less significant relative to the already powerful gravity from the normal matter.
Okay, and the flip side.
Conversely, out in the regions where the density of detectable standard matter is very low, like the faint outer edges of a spiral galaxy, far from the core.
Where normal gravity should be getting much weaker.
Yes, where Newtonian gravity is dropping off rapidly. In those regions, the extra gravitational effect generated by alpha becomes larger, more dominant.
Wait, that sounds backwards. Why would the extra gravity effect be weaker where normal gravity is strong and stronger where normal gravity is weak?
Think of it like this. Maybe in the dense galactic center, the gravitational field is already so intense due to all the stars and gas that the modification effect from the varying constants is somehow saturated, or maybe just less noticeable compared to the immense gravity already there. It's like trying to make a small ripple in a storm-tossed sea. The effect is negligible.
Okay.
But as you move outwards, the gravity from the visible matter falls off dramatically. Remember the inverse square law? It gets weak very quickly.
Right.
At that point, the modification effect, this gravitational imposter alpha, generated by the local spatial variation of the constants in that low-density environment that becomes the main player influencing the orbits of the outer stars, its relative contribution becomes much larger.
So the modification effect kicks in most strongly, precisely where standard gravity predicts things should be slowing down, but they aren't.
That's the claim. It's not about adding mass. It's about the geometry of the gravitational field itself being altered. And that alteration is most pronounced where the gravity from normal matter is weakest.
And that altered field provides the extra pull needed to keep those outer stars moving fast, explaining the flat rotation curves.
Exactly. It generates the required extra force without invoking any new exotic dark matter particles or halos. It's presented as a unified fix, using just the dynamics of known forces and constants.
It really all comes down to accepting that foundational premise, that the constants of nature aren't truly constant over cosmic time.
That's the linchpin.
And if you accept that, wow, the implications just ripple outwards. It doesn't just change what the universe is made of, it changes how old it is, maybe even where we should be looking for answers.
Absolutely. And one of the first major implications addresses a real headache in standard cosmology, something that's become even more apparent with recent observations.
You mean the age puzzle?
The age puzzle, exactly.
Yeah.
Or it's sometimes called the impossible early galaxies problem.
Right. This is about telescopes like James Webb finding these incredibly massive, well-formed galaxies surprisingly early in the universe's history.
Stunningly early. JWST keeps sending back images of galaxies that look remarkably mature, massive, structurally complex, existing at very high redshifts. That means we're seeing them as they were less than 1 billion years, maybe even just a few 100 million years after the Big Bang.
And under the standard timeline?
Under the standard lambda CDM timeline, which puts the age of the universe at about 13.8 billion years, there just doesn't seem to be enough time for gravity to pull matter together, let it cool, form stars, and assemble these huge ordered structures so quickly.
It's like finding a fully grown ancient oak tree just weeks after planting an acorn. Standard physics struggles to explain that rapid formation.
It's a real tension point. How did structure form so fast?
So how does Gupta's evolving constants model, CCC plus TL, help with this?
Well, remember how the model combines covariant coupling constants and tired light. That combination fundamentally changes how we calculate cosmic distances and timescales based on redshift.
It recalibrates the cosmic clock.
It effectively stretches out the entire history of the universe. Gupta's specific calculations based on CVC plus TL suggest the model almost doubles the inferred age of the universe.
Doubles it. Wait, from 13.8 billion years to...
Roughly 26.7 billion years.
26.7 billion years. That's That's almost 13 billion extra years of cosmic history.
It's a monumental difference. Suddenly, you have vastly more time in the early universe.
And that extra time?
That extra time provides ample room for the standard processes of gravitational collapse, cooling, star formation, and galaxy assembly to happen gradually. Those massive early galaxies seen by Webb are no longer impossible. They just had almost twice as long to form as we previously thought.
So the universe becomes older, maybe calmer, more patient in its evolution.
Exactly. It allows for passive evolution over a much longer timescale, which fits naturally with the observations without needing exotic, superfast formation scenarios.
That's a really compelling point. It connects two seemingly unrelated big problems, galaxy rotation and early galaxy formation, and potentially solves both with the same shift in fundamental physics, the evolving constants.
It's a strong argument for the model's coherence, yes.
Okay, but let's talk about the practical side, the so what for science today. If this theory turns out to be right, or even partially right, what does it mean for all the effort going into searching for dark matter particles right now?
That's the potentially enormous consequence. If the effects we attribute to dark matter are actually due to gravity behaving differently because constants are evolving,
then there's no dark matter particle to find.
Correct. No WIMPs, no axions, no exotic particles making up these halos. It would imply that the massive, incredibly sensitive experiments built deep underground.
Like the xenon detectors trying to catch a WIMP bumping into a nucleus.
Exactly. Those experiments, costing billions of dollars and involving decades of effort, might be searching for something that simply doesn't exist in that form. They could be looking for a ghost conjured by our assumption of constant physical laws.
Wow. Think of the resources, the scientific brainpower focused on that direct detection effort. If this alternative is correct, that effort might need a major redirection.
It would fundamentally shift the focus of particle cosmology and astrophysics. And this brings us back to that idea of simplicity, the principle often called Occam's razor.
Right, the idea that the simplest explanation is often the best. How does Gupta frame his theory as simpler than the standard lambda CDM model?
He makes a pretty stark quantitative point. He argues that even if scientists do eventually detect some new exotic particle that could be a dark matter candidate.
Which hasn't happened yet, despite decades of searching.
Right. But even if they did, to explain the astronomical observations, the galaxy rotation, the cosmic structure that dark matter would need to account for about 85% of all matter in the universe. That means it would have to outweigh all the normal matter, protons, neutrons, electrons, by a factor of about 6 to 1.
So you'd have to accept that for every one part of the stuff we know exists, there are 6 parts of some completely different, invisible, exotic stuff dominating the universe's mass budget.
Exactly. You have to invent this enormous amount of unseen substance just to make the standard equations work with constant laws.
Whereas the CCC plus TAL model,
the evolving constants theory argues it's simpler. It doesn't invent new substances. It proposes a modification to the behavior of the substances and forces we already know exist, driven by their interaction with the evolving universe itself. It uses the 5% of visible matter plus changing rules to explain the observations attributed to the other 95%.
It shifts the burden. Instead of finding new ingredients, we need to rigorously test if the fundamental rules themselves are stable.
That's the core argument for its elegance. Test the foundations before adding vast, unseen complexities.
Tying this all together, then, it really suggests a potential paradigm shift in how we even approach physics, doesn't it? Maybe moving away from adding new particles or fields every time there's an anomaly.
Yes, away from what some might call ad hoc additions.
And focusing instead on whether the laws and constants we've assumed to be absolute might actually be dynamic, variable, evolving with the universe.
It forces us to question our most basic assumptions. For centuries, the constancy of constants has been bedrock. If that bedrock is actually shifting, even incredibly slowly, then our whole understanding changes. When we look billions of light years away, we're not just looking back in time.
We're potentially looking at a universe operating under slightly different physical rules. Gravity might have been stronger or weaker. The speed of light might have been different.
Precisely. And that means every distant observation needs to be interpreted through that lens of potentially changing laws. It adds a whole new layer of complexity, but maybe a necessary one.
Okay, so summing up this deep dive, the core takeaway is pretty mind-bending. The biggest mysteries in the cosmos, dark matter, dark energy might not be about hidden particles making up 95% of reality.
They might be cosmological illusions.
Tricks played on us by the incredibly slow, subtle evolution of nature's fundamental constants over billions of years. The universe isn't necessarily filled with invisible stuff. Maybe it just plays by slightly different rules over vast distances and times.
And the appeal is that it offers potential unification. It's a single framework, CCC plus TL, that attempts to explain galaxy rotation, large-scale structure, light bending, and cosmic acceleration with one consistent physical idea: evolving natural forces.
It provides that potential aha moment, suggesting maybe the underlying reality is simpler than the complex lambda CDM model implies.
It challenges the standard model across the board, from the smoothest cosmic scales down to the details of individual galaxies.
Which brings us to a final thought, something for you, the listener, to really chew on. Professor Gupta finishes his paper by saying, sometimes the simplest explanation is the best one.
A classic appeal to Occam's razor.
But this whole idea of evolving constants raises a really profound question about the future, doesn't it?
It absolutely does. If the fundamental forces, like gravity, are indeed weakening over cosmic time, which is the engine driving this whole CCCT plus TL theory, what does that actually imply for the ultimate fate of the universe?
Our current predictions, things like the big freeze or maybe a big rip, they all depend heavily on how dark energy and gravity behave now, and assume they'll continue behaving that way forever.
We assume the current strength and laws are static over infinite future time.
But if the forces themselves are constantly evolving, weakening, then how reliable are those long-term predictions? How much of our physical reality is defined by laws that are fundamentally transient, not fixed?
It introduces a kind of unpredictability, or at least a dynamic nature, to the deep future. Are the rules of the cosmos written in stone, or are they more like a living document, constantly being revised by the universe itself? It certainly gives you something to think about.